Next, we have a CFA assignment. So CFA stands for Confirmatory Factor Analysis. So this might be the follow-up to an exploratory factor analysis. So this would be the first try at CFA and looking at how to code them in Lavaan and how to create pictures of them, how to work with a standardized solution, how to work with a data set, full data set this time, since all the other class assignments have included correlation or covariance tables. And so we're going to get into how to program this first. Right? So we're going to use a scale called the Computer Aversion Attitudes and Familiarity Index, or the CAFI, by Schulenberg, who's a friend of mine. And all of these questions are about different issues with computers, so I don't like them, I think they're a good thing, I'm familiar with using them, and what we're going to do is program the three-factor model that he found in his original exploratory analysis, and then we're going to try a one-factor model, and then test and see if those models are different from each other, and look at some residuals, so this should just say residual here, not standardized, modification indices, loadings, and fit indices. So let me load up RStudio here. Yes. Let's see, let me close everything out. Had some stuff I was working on for the last video still open. Alright, so let's go to new script. Remember, the first rule is always to load your libraries, so we're going to use Lavaan and Simplot to create the pictures of the analysis. Now, the first thing I'm going to do is load the data. So this time I have real data instead of a correlation table or covariance table. And it's saved in a CSV file, so I can use this import dataset option. Let's go import dataset from text file. And all of these files will be available soon on our website, statstools.com. And let's see here, where do I have that scrolled away? Structural equation modeling, assignments, and there we go, CFA basics. Now, when you use this window, make sure you always check down here when it shows you how it's going to come out in the data frame. So I'm going to rename mine to something simpler like data, but you want to make sure that the first column where all your variable names are is actually the variable names you want to use. So I'm going to turn on heading, so I get question 1, question 2, question 3, and not character columns with question 1 as the first row of data. SPSS will import this in the same types of ways, so you always have to make sure that it realizes that the first row of data is the names of the variables and not just another row of data. Okay. Lots of other options, but I don't need them, so I'm going to hit import. And then I always cheat because I can never remember the paths for things. Now you could set your working directory instead of using a very specific path in case you wanted to move it. But for right now, this will work for us. Right? So I've got my data set imported. Now I want to create the models. So let's start with a three-factor model. And so the three-factor model is going to have a specific set of questions. So let me copy that from Word over here. And then go back to Studio. Okay, so I'm just going to kind of temporarily plug that into R and use that to create my three-factor model. So familiar is approximately, so I'm going to do equals approximately, and so that's new. What is that, if you've been watching these videos in order? So before we've just been using a tilde, and it's this y variable is approximately these x variables added together. Well, now what we're doing is we're creating a latent variable. So with confirmatory factor analysis, what you're trying to do is show that there are specific latent variables that affect the questions, or the manifest variables. You can call them items or indicators depending on which book you're reading. And so it's basically like, if you think about this as computer familiarity, is what causes the answers on my questions. So I want to build familiarity with these questions, but since this is a confirmatory factor analysis, we want it to be reflexive so that the latent variable predicts the questions. And so this allows us to say that yes, familiar is x, and it is approximately equal to all of these other things added together. So not only does this create us a latent variable that isn't in the data set already, it also allows us to say this variable predicts all of these other ones. So I'm going to type in my question numbers, and if I'm looking at the data, I have them labeled fairly easily, so it's Q1, Q2. And so I'm going to look down here at what the items are. So it's Q3 plus Q13 plus 14 and 16. You would wish you could do, the spacing doesn't matter, I'm just trying to keep it nice and neat. Q20 colon Q23, that would be great if it was actually base R, but it is not, so you have to type each one individually. Oops, don't leave off a number, it'll be very confused. 30. Now, one thing you want to make sure that you don't do when you're doing this is name a variable with a number. I don't think R will normally let you do that in any kind of way because it thinks of numbers as numbers. So I can't just have this be 1, 2, 3, 4, 5 like you would want to do because it would assume I literally meant to add 1, 2, 3, 4, 5. And so it would think that you were trying to add some sort of intercept. So starting it with Q1, Q2 will sort of help. In general, starting with a number is not a good idea. And then you actually cannot name them solely just numbers. Oops, forgot a plus there. 18. I would say tell me when I make a mistake, but this is a recording. 29. Oops, Q29. Okay, so I got my second one. Now aversion here is approximately equal to, let's go question 6 plus question 7 plus question 9. It's question 10. 12. Ooh, not capitals. There we go. Okay, so, phew, got all that typed. Now, I don't have to include, a traditional CFA is going to include the correlations between the latent variables. Remember that Lavon will do this for you. So this is my three-factor model. I didn't get rid of that uppercase Q. There we go. Now to program a one-factor model, I'm going to do the exact same thing, except this time I'm just going to make everything computers. So I'm going to copy this so you don't have to suffer through watching me type all that again. And what I'm going to do is delete this, put all the questions on one line, because I want them all to be predicted by the same variable. And I'm going to just call that computers. So we are saying that there might be a three-factor model with familiarity, attitudes, and aversion, or it might be just one giant one-factor model. So I've got my models created. Next thing we're going to do is run the models. Well, let's see what I asked for because I can't remember. So we're going to include a picture with the standardized loading. And then we're going to check for some different things. So for Haywood cases, we want the squared multiple correlations. And then we're going to look at the loadings, the residuals, modification indices, and fit indices. Okay, we can do those one at a time. So let's start by running the models. Okay, so we got 3 model, let's do 3 fit and 1 fit. And this time we're going to use the CFA function. Okay. And the CFA function is a little different from the sim function, but not by a lot. Okay. So when we're looking at sim in the Lavon library, there are lots of different options, and we've been working with model and covariance structures and stuff, and you can use fit indices, that sort of thing. But in the CFA, it looks pretty much the same, right? But since we're doing a CFA, it helps if you use the CFA function, because that'll kind of help you remember, but I don't know that there's really that big of a difference between them. Okay, so the first thing you gotta do is tell it what model you want to use. So let's use 3model fit 3model for this one. Okay. I'm gonna do my data equals data. So this time I'm not gonna use sample.cov because I don't have a covariance table. I have the raw data, so I'm gonna go with the entire data set. Now, that's all you really need, and that will run a confirmatory factor analysis and give us this 3-factor model. So let's now do the 1-factor model. Give that a second to run. Great. Now let's create the pictures first. Let's see if that did what we expected it to do. Okay, so I'm going to use SimPaths because it'll work on the CFA created models too. So I'm going to do 3.fit. Let's do what labels equals. Okay, and this time I'm going to do STD for standardized solution instead of PAR for parameter for unstandardized solution. And the layout for this one that works best is tree. All right. It's loading slowly. There we go. So it's all crammed down here. So I'm going to hit zoom. So the first thing it did was it gave me my 3-factor model, and it really squishes them all together. But I can look at how, that's a funny abbreviation, it's unintentional. I can look at the standardized solution, which makes these correlations out here. So you see variance is standardized and set to 1. The dashed line means that my scaling was set on the manifest variable. And so it actually didn't estimate this parameter. It set it to 1 to use to scale it. But here's the answer if it were in the standardized solution. The correlations between these three are pretty moderate to high. So a 1-factor model may fit pretty well because they're so highly correlated. Or it may be a second-order model, which is the next assignment. Okay, so if you're interested in second-order and bifactor models, watch the next video. All right, and I can't really read all these paths, so I would have to look at them individually, but it looks like it did it right. I mean, it looks like what I would expect. They're correlated with each other, that sort of thing. So let's make the other one. I'm going to use basically the same code, just trade out for the 1-factor model. There we go. So for computer, I got everything tied to it. Right? So that looks like it created pictures that I would have expected. All right. So I have done this create 1-factor model, include pictures with standardized loadings. Cool. So for this 3-factor model, let's check for Haywood cases. So what are Haywood cases? And I'm pretty sure it gives you a warning when you get Haywood cases, but it doesn't hurt to know what they are so that you can sort of know what to look for. So a Haywood case is an improbable solution because your squared multiple correlations, or R squared, are over 1. Now in Lavon it's called R squared, and that's pretty appropriate because it's the amount of variance accounted for in that question, or item, or latent. And but every other book that you'll see will usually call them squared multiple correlations. If you're using a different program, that's what it's labeled as in the output. Okay. The other thing to look for is negative error variances. Okay, so variance cannot be negative because it's squared in the formula, so it's mathematically impossible. Covariance can be negative. So when you're looking at the relationship between latents, that can be negative, but error variances cannot. Okay? And those are labeled variance on the output. So let's do a summary of our 3-factor model to answer that question. Okay, so this will be our summaries section. So we use a summary command, and let's do that on 3.fit. Now, to get the, we've been talking about how you want to do the standardized solution. So standardized solution is true. So I can look at the different versions of a standardized solution. And then to get the square multiple correlations, the code is r square equals true. All right, so let me look at this output here. Now, here are a couple of different things about scaling. So if you don't do anything in the CFA command here, it will automatically scale the variables based on making one of the manifest variables, the first one, set to 1. And you'll see that here. So this is the unstandardized solution here. And so these are interpreted as regression paths. So for question 13, every 1 unit increase in familiarity, I get 0.88 increase on question 13. So that's easy to interpret when I think about how the scale works. Standardized latent variable, this column here, instead switches the scaling to the latent variable and forces the variance for the latent variable to be 1. Okay. And so those are just two different ways to scale. And so kind of my opinion is that unless you specifically need to standardize for the latent variable, is to not. To set the manifest, let it automatically do manifest scaling for you, and then you can get both of them by turning on standardize as true. And so I could look at either one. So this one gives me more options. If I automatically set standardized to the latent variable, I only can see one of them. So I kind of like more information than less. Standardize all is really useful because it standardizes on both ends. And what that I think is useful for is, since we're doing confirmatory factor analysis, you are probably have already run an exploratory analysis, and standardize all will let you see it in the same scale that you would expect for an exploratory analysis. And so when you're looking at, do questions load over 0.3, which is kind of the rule for EFA, this will give you that same scale. Whereas if I'm looking at the unstandardized solution, I can get a 1.3, and you think you've screwed something up, and you haven't, because that's in the scale of the data. So it's 1.3 points increasing when familiarity increases. And the same problem over here, standardized versus on the latent, is sort of like a z-score. And so that doesn't necessarily give you that in the same scale, but standardizing everything gives them to you kind of like EFA. So that's why I like that option. Honestly, there's nothing wrong with any of the options. Just tell people when you're working on writing this up which one you did, and so they understand why your parameters are what they are on your picture. Okay. Anyways, back to the Haywood question. So I'm going to scroll down a little bit. Now, see how this is labeled covariances? Those can be negative. None of them are, but they could be. But now I'm going to come down here to variances. So these are my error variances for each question. I just don't want them to be negative. Okay, they can be large, but I just don't want them to be negative. And so none of them are, so that's good. And then the last thing down here is r square. So how much variance is accounted for in each question by the latent variable. And while some of them are not the best, we want it to be really high, right? None of them are over 1. Okay? So we don't have a Haywood case in this instance. Okay? So you want to check and make sure your SMCs are not over 1, your error variances are positive, and then you are good. All right, next question is, what about the item loadings? So we would expect questions to load onto their factors, right? Or you'd hope they would. So I'm going to go back up here. And this is what I was saying, why I would like standardize all. You could check the p-values, they're all significant, but sometimes it's not super helpful because when you have large samples, everything will be significant, even if it's really tiny. So, it might be statistically significant, but not practically significant. And their loadings are sort of like an effect size. So you can look at those to see if they are indeed loading in a way that you would want. So you can kind of use the 0.3 rule as a criterion. And they do look like they're loading pretty well. If anything, I would say some of 18 and 19 may not be very good questions for attitudes. Although they are still over our cutoff, kind of informal cutoff. And so I would say all the questions are doing what I would expect, right? So they don't seem too bad. You could also look at R-squared, but R-squared will tell you the same thing that the loadings do. So things with really low loadings will give you low R-squared values too. Okay, so we're only accounting for 14% of the variance. If you use traditional R-squared, there's sort of two sets of rules for R-squared, and so it's either 1.01 is small, 0.06 is medium, and 0.14 is large, or 0.01, 0.09, and 0.25. This is somewhere between medium and large. Oops, we want to go back to Word here. Alright, so no, not really. Now, residuals is a way to look at where the fit maybe is not matching. And so we can look at a residual correlation table to see what some of the fit problems may be. All right, so let's do that. Okay, so I'm going to show you two different ways to do this using the residuals function and kind of give you a hint on how to make this easier for yourself. So let's do correlations, so the residual correlations. And so what you do is I'm going to call this correl to give me the correlation table. So I'm going to save it, and you'll see why here in a minute. I'm going to use the function residuals. So I want the residuals of 3 fit, which is where we saved our CFA. And I want to give it a specific type, otherwise it does covariance automatically. So covariance is unstandardized, so I don't know how to interpret those. I don't know what a bad score would be, so let's do core for correlation. Okay. So if I run that, it gives me a list over here. So instead of just giving me the correlation table, it actually gives you a couple pieces of information. So let's view it by typing correl down here. And when you have 30 questions or more, this correlation table is huge. So you'd be like scrolling through and it's just tons of stuff here. But the correlation table, you can see here, is saved under core. So what I can do is view the correlation table. Now remember, the view function is one of the weird ones where it's a capitalized letter. I want to do correl, and this is subsetting from a list. So I'm going to use this $, and I want core. And that will give me the option to see the correlation table. Now, if you're using Studio, the great thing about that is it pulls it up here in the editor window, and it gives you the option to sort them. If you do not have this option, update Studio, because I didn't ever have this option on my Mac until I updated recently. Right. So I could flip through and look at the bad combinations. So question 3 has a couple of negative pairings with these questions that aren't so good, and then a couple of positive ones. Okay. And so the same issue, I would scroll through each one and kind of look for the really bad spots. I saw one there. Yeah. So question 14 and question 23 are not playing along with each other. Because look how high that correlation is. That's half, that it just cannot figure out what the difference is. Also over here on question 21. So it's looking to me like question 23 might be kind of problematic because there are lots of times where it has a high residual value. And so really this will tell you where in the correlation table you might be having some trouble with fit. So it might be one particular item has a bunch of really high residuals, or it might be that one factor has a bunch of high residuals, and that can give you some clues as to where you might be able to edit it or take a closer look at what's going on. The problem with using correlations is while they are standardized, they don't really have a cutoff score. I mean, I would say, 0.1 is going to be kind of bad, but there were a lot of them that were at 0.1. We haven't looked at the fit indices yet, so I don't know if this model fits. So let's give it a more traditional view, and let's make it a z-score. So let's do z-correl this time. Residuals, okay, and I'm going to do the same thing I did above, 3.fit, and now type is equal to standardized. There's also another option which is normalized, and it has a discussion about this in the help guide for residuals for Lavon. And essentially the difference between standardized and normalized is just a math issue. Most people are going to use standardized, but if you get a bunch of NAs, it suggests try using normalized instead. So standardized means make them z-scores. So I'm going to save that. And let's try viewing that one now. Okay, so I have view, z-coral, $, and now my options are type, cove, and mean. So you want to use cove. Okay. Why are they different? I don't know, they just are. Okay. Now these are z-scored. So since they're z-scores, anything over 1.96 is statistically significant at the 0.05 level. If you want to be more stringent, you could use 2.58 for 0.01 or 3.23 for 0.001. I see we did get some NA values, but look at this, 13. Good gracious, that's out of control. And so I think mostly the NA values are when it's correlated with itself. So that's not too surprising because you can't z-score zero residual. Okay. And so I would look for, okay, well, it did give me 0 here. So I don't know why sometimes the NAs are happening. I would look for a question that reappears a lot with significant, what we would normally consider significant residual correlations, z-scored. Okay, so that's how you'd look at them. And it kind of looked to me like question 23 is a culprit here. So it's got a bunch of high values. Now it has some that are normal, but most of them are pretty bad. So I might consider taking question 27 out. I'm sorry, 23. And we knew from before that 19 wasn't fitting very well. So let's look at 19. And it has some, but not a whole lot. So it may not be the question you expect. Let's put it that way. Okay. All right. So that's how I can look at the standardized residuals. Okay. Are there any modification indices? Okay, so we haven't talked about how do I get those. Now, part of the summary could be mod indices equals true. But instead, what I'm going to tell you to do is tell you to do it separately, because then you can kind of, you can add more arguments to it. If you add it in the summary function, you're sort of stuck with seeing every possible modification indice, and it's just this huge table. If you do it in the separate function, you can look at, you can sort of set some rules. Okay. So we want to do the mod indices for 3fit. Okay. And let's do, it's sort with a dot, so that's a little odd, but I want to use that. Let's do sort equals true, so that the highest ones are first. And then just run that, and we'll come back to minimum value here. Okay. So I'm going to do that. Give it a second. So I got 561 of them. Lots of them are zeros. Look at all the stuff. So much stuff. Right? Oops, scrolled too high. There we go. And so, but it did sort them in descending order for me. If I look at the MI column, I'll explain what that means in a second. But I can clearly see that there are 500 of them. And so let's create a lower criterion. So I could do minimum value here, and I could say only give me anything that's over 30. And that is just because I'm looking at the numbers already and I know there are lots of them. You could use 3.84. That is the chi-square cutoff for 1 degree of freedom. Okay, sometimes called the Lagrange multiplier. So let me cut some of those out. Basically, using the sort function and the minimum value just help you see only the biggest ones. Okay, if you're wanting to see specific paths, that's when you might need to just leave all of them on and kind of scroll through them. All right, so what is in this output? Well, the first thing it gives you is actual code that you would use to include this in your model. So you can cut and paste it, so that's nice. Now this is a double tilde, so it's a covariance between question 14 and 23. So you'll tend to see things with high residuals pop up here because you're trying to account for those residuals. So if I added a covariance between question 14 and 23, I would get a change in chi-square of 372. Okay, so MI is modification indice, which is how much the minimum fit test statistic is going to change, or chi-square, if you add this exact path to the model. Okay. I don't know if the rest of the columns are super important, but it's expected change and then some standard errors for those. So that's expected path change, I think. But generally people look at like how big the chi-square is going to change, because usually you're trying to do this to improve model fit. Now, it will suggest things based totally on math. And so you want to make sure these are things that theoretically make sense. So at least, in the social sciences, we're really focused on theory building and model testing based on those theories. And so I don't know if I should correlate those questions. I would need to go back and look at the questions and see if, like, okay, the reason why we're getting this is because the error terms on those are really correlated, because they're really similar. Maybe I should consider excluding one of those questions because they're just way too similar. So that's why we're getting so much error there. Right? The other things it'll give you are some what we would normally consider cross-loadings. So it's saying that question 8 should also load onto aversion, which I don't think it currently does. So let's go back and look up here my model. Question 8 at the moment currently loads on attitudes. And so it's saying add a path from aversion to question 8. So it should also be on this factor. And then there are some folks who say that you should never let questions cross-load, which means load on more than 2 factors. And that's very traditional EFA simple structure rules. And then some people say it's fine. So that one you're just going to need a really good reason and hope you don't get one of those really staunch reviewers that doesn't like that sort of thing. And which will likely happen to you either way, from experience. All right, so that is how I'd look at the modification indices, and I can add these paths to my model pathing up. My model creation up here, and then I would just rerun run the models, run the picture, and I could rerun this code I've already used. Okay, so that's how you do modification indices. All right, the last thing is let's look at fit. You can include fit in the summary command. And we actually haven't run a summary of the one fit model yet. So let's do that. All right, so let's see if things load on this. Okay. So they all appear to be statistically significant. Let's look at the numbers here. Ooh, this question's bad. So question 21, not so much. Question 23, this should not surprise you given what we've already looked at. I would argue are probably bad questions, okay, given the very low standardized all scores that they have. Okay. I don't appear to have any Haywood cases, so all my variances are positive. And all of my r-squareds are less than 1, but look at 21. I mean, good gracious, that's tiny. So we're not doing a very good job with that question. And you'll notice that all the r-squares tend to be a little lower. So I'm going to imagine that the 3-factor model is going to fit better. So we could use fit.indices or fit.measures equals true in the summary function, or I could do it separately. So it's fit measures, and I want to do the 3fit. And so I'm going to pull all the numbers I need from here for the 3-factor model. I like separating them out so I can see which piece of information I want to look at one at a time. So I don't have to like kind of scroll through everything and find it, but to each their own on that one. Right. So I got chi-square here. So I got 2874.75. Okay, the degrees of freedom are 402. Okay. That is clearly going to be significant, which is not a helpful number. I'm going to ignore my baseline chi-square because I don't need it right now. My CFI is 0.737. My TLI is 0.716. I often like to include NFI. You can also, if you don't like AIC, include ECVI. Pick your favorites. Just don't pick any of the goodness of fit statistics because they're terrible. So if I come down here to NFI, not double N, it's 0.708. So I don't need any of those. Scroll, scroll, scroll. The AIC is 73216.719. Okay, so it's right here. Let's see, here's my RIMC, so 0.088. My 90% confidence interval is 0.085 to 0.091. So that's a good sign because that's all in the acceptable range. There. Alright, so my SRMR is 0.087. Then if I wanted to include ECVI, it's the last one, 3.779. Because I'm going to do some model comparison here. Alright, now, which ones should you report? Chi-square, RIMC, SRMR are pretty much a given, I feel like, especially in our field. CFI is very popular. I might tell you to pick one of the comparative fit indices. So CFI, TLI, and NFI all fall into that category. There's also IFI and RFI. You know, there's lots of them. If you're going to do non-nested model comparison or any type of model comparison, you can use these for nested models too, is AIC and ECVI. So Akaki information criterion and the expected cross-validation index. All right, let's get the one-factor model here. Give me a minute to think. Alright, so here we go. Let's look at, so we got chi-square, 4486.874, so already not doing good because chi-square has gone way up, almost doubled. We've only really changed 3 degrees of freedom because we collapsed all those covariances into one. My CFI went from kind of like not so hot to like really not so hot. Okay, so those are all not acceptable. Of course, the 0.7 ones aren't really that acceptable either. My AIC is this number, which I'm going to cut and paste instead of trying to type it. Okay, so the first model's AIC is lower, and you always want that to be lower. Okay. For my RIMC, I've got 0.113. My 90% confidence interval is 110 to 116, so that is not in the acceptable range. SRMR is 107, and ECVI is 5.802. All right, so which model's better? It doesn't take a whole big chi-square table to tell that a 3 degrees of freedom difference in nearly 2,000 points is significant. So clearly these models are different. The change in CFI is greater than 0.01. That's the criteria for that one. And then the AIC and ECVI is whichever one is smaller. So clearly the 3-factor model is smaller. So while the 1-factor model is more parsimonious, it's the simpler model, the 3-factor model has clearly got a better fit. The loadings are better, although there are some problematic ones, and the fit indices are better, even if they're not perfect. So I would argue that the 3-factor model is much better than the 1-factor model because the fit indices are better and the loadings are better, etc. And so then I might start to explore the modification indices to see what's going on, or maybe deleting questions and seeing if if there are outliers or problems with the question that maybe are causing poor model fit, and rethink maybe how the questions are loading or if they should be on there at all. So all of that taken together is sort of a basic idea of CFA. The next assignment covers second order CFAs or hierarchical CFAs and bifactor models, where you split the variance into a generalized factor and a domain-specific factor.